Sure. So if you recall the thing that we finished with last time, let me just do a quick revision of stuff. So a Poisson process is a process where the inter-arrival times are exponential, right? So people are walking into a store. The inter-arrival time or the time between two people walking in is an independent exponential random variable. And you look at how many people have arrived until a certain time t. That is a number that you call as nt, which is a random variable. And that is the Poisson process as t varies, right? And as we saw, nt turns out to have a marginal, which is Poisson with parameter lambda t. Furthermore, nt is a Levy process, right? In other words, nt n0 is 0. Nt has independent increments. So if I take two different disjoint time intervals, the number of arrivals in each time interval is independent. And finally, the number of arrivals in any time interval only depends upon the length of that interval, right? So nt minus ns only depends upon t minus s. And it's because of that, it is nothing but a Poisson lambda t minus s random variable. And we saw a proof of this as well. After seeing a proof of this, we went directly to stochastic integration. But oh yeah, before that, we also saw that nt minus lambda t is a martingale. So nt itself is not a martingale because its sample paths are constantly increasing. So it is not fair by any means. But nt minus lambda t, what it does is it makes sure that in between these jumps, the process is going down. So wait, let me draw it more accurately. So it's something like this, right? So it's something like it goes down in between jumps, and therefore it remains fair in some sense, right? We also saw that you can, so this Poisson process has different kinds of self-similarity. Today, we'll actually see an interesting example of marked Poisson processes. So let me quickly explain that. If you have a Poisson process, and suppose you mark every good as bad, every jump as either good or bad in your context, and suppose good and bad jumps occur with certain independent probabilities, then the good jumps and bad jumps by themselves alone, they form independent Poisson processes with appropriate intensity, right? And you can, of course, generalize this, which is what I will be proceeding to do today. We also saw that stochastic integration is super easy with respect to processes which have piecewise constant paths and therefore are right continuous with left limits. For any such process, integral f dg is literally nothing but summation of f delta g. So to integrate a function over of another one, which is piecewise constant with jumps, you just sum at all the jump points the value of the function times the value of the jump. That's it. So integral f dg is summation f delta g. And therefore, for a Poisson process which only jumps by 1 at each jump time, you just get the sum of the values at the jumps is equal to the integral with respect to the Poisson process. Then we finally came to compound Poisson processes, where we talk about not jumping by 1 each time, but by jumping at a random jump with a particular fixed distribution each time, right? So JS. This is a so-called compound Poisson process. This is also a Levy process. And as we saw, this process is a martingale. So xt minus expectation j times lambda t, this is a martingale, right? So when j is 1, we just have the typical Poisson process. So j is 1 all the time. And there you just get xt minus lambda t is a martingale. Right. Now, what is a pure jump process? A pure jump process has piecewise constant paths. It has right continuous paths. So at any jump, you ensure that it is right continuous and not left continuous, right? And we also assume that xt only jumps finitely many times between any two jump points. That was also true, right? Now, for any such process, doesn't need to be Markov, Martingale, Levy, anything. We can define integral xs djs as just summation xs delta js. So it is not so difficult. Now, what is a jump process? A jump process has three parts. It has a Brownian motion part, it has a continuous drift part, and it has a jump. Right? And because we know Ito integration, we can integrate any process with respect to any process which has these three components, or with basically with respect to any jump process, right? And the answer to that question is pretty obvious. You integrate separately with respect to the Brownian motion, separately with respect to the drift, and separately with respect to the jump. So in Ito notation, this is exactly what it would look like. If you have dxt, which is given by gamma t dbt, theta t dt, and djt, so this is the jump part, then you just multiply phi t on all sides, and you literally get what the stochastic integrals break up, right? So phi t dxt is phi t gamma t dbt, phi t theta t dt, and phi t djt. Now the question was, when was this a martingale? Well, we took an example where we computed phi t dxt, where phi s is exactly 1 if the Poisson process jumps at that point, otherwise 0. And xt is this martingale that we had seen earlier, nt minus lambda t. We computed through the typical, rule that this thing is exactly equal to the Poisson process itself. So phi t dxt was equal to dnt. So what you can see from here is that phi t dxt, even though this is a martingale and even though this is adapted, a stochastic integral with respect to a martingale doesn't end up being a martingale, because it ends up being the Poisson process, which is clearly not a martingale. So what do you need to do in order to adjust for this? Unfortunately, we need to have one more condition on phi, right? And just to summarize what all we're going to do today, we're going to start with stochastic integrals as martingales, and then we're going to go to the Ito formula, followed by the Girsanov theorem. That is what we're going to do today. So very quickly, if Bt is a Brownian motion and gamma t is an adapted process, we know that integral gamma s dbs is a martingale. So this is true. But what do we also know? We also just found out from our last example that adapted is not enough for jump processes. And what do we need? From a finance perspective, we found that yesterday a stock value, if it's performing like a martingale, then suppose that I am a very smart investor. What I would do if I were able to predict the jumps is to just sell my stock before each jump, or sorry, buy the stock before each jump, just before each jump. And then right when it jumps, if it's a bad jump, you would sell it immediately after the jump, right? So if I know when the jump is coming, then I can time the market perfectly and I can gain arbitrage out of this by selling whenever I know a good jump is coming up and buying just after that. Or sorry, the other way around. When buying whenever the price is low, and then when the price jumps, I'll sell immediately. Or if I know that the market is going to go down, I'll sell immediately. And then just after the jump, I'll, right? So either way, regardless of whatever the situation is, if I know a jump is going to happen, predicting the jump should allow me to get arbitrage. But unfortunately, time fundamentally is a non-left continuous object, right? So I just do not know when a jump is coming. And the fundamental thing is, if I do not know when a jump is coming, I should not be able to gain arbitrage out of it. So therefore, I require left continuity of phi s. The way my portfolio behaves, which can only adjust with respect to what I know right now, cannot predict jumps, and therefore I need my portfolio to have left continuity built in. And the final theorem is that if you have a jump process, which is a martingale, and you have a function which is a left continuous adapted process. So this left continuity you can see over here is coming. Then under this integrability condition, this guy is a martingale. The proof is skipped. It just, what you do is you consider left continuous simple functions and then you approximate, right? So what we'll do right now is we will actually take an example where there is a left continuous simple function, which we will be considering. And we'll see that the stochastic integral with respect to it is a martingale. But if we consider the natural right continuous analog of that same process, we will lose the martingale property. So what is the example that I have? Suppose that you're running a Poisson process and you let S1 be the first jump time. Okay. So the question is that if you are having this guy and you let phi s be 1 up till that jump point and then 0 after that, then the question is, yes, this is left continuous, right? Because this is up till S1, it is continuous. So it is continuous from the left. It is 1 even at S1. But after that, it's 0. After that, you're in trouble, right? So this is a left continuous process. And what would be the right continuous version of it? The right continuous version of it would be indicator 0, comma open at S1 of S. Because then at the point S1, it would be right continuous, but not left. So we'll check now what is the integral, stochastic integral of this guy with respect to ns minus lambda s. Let's do that. Well, same old, right? To do a stochastic integral, what would you do? Well, d of ns minus lambda s, break it into the drift part and the Poisson part. Once you've broken it with respect to the Poisson part, you get this drift and you get this Poisson part. Now, let us see what is the value of what is going on over here. We have to deal with 3 categories. What happens if t is less than S1? What happens if t is equal to S1? And what happens if t is greater than S1, right? Now, if t is less than S1, then if you think about it, here phi s is 1 and the second term is 0 because n hasn't jumped yet, right? So if t is less than S1, then this quantity is nothing but integral 0 to t lambda ds plus 0, which is nothing but minus lambda t, right? Because of this negative sign. So up till here, it's negative lambda t. Then after that, the second term, so what happens at t equal to S1? And this is where things are very important. At t equal to S1, the first term doesn't increase because it's an integral over ds, right? So if it's an integral over ds, then an integral over ds cannot increase if you just change the value at one point. But if you have a jump that is taking place, then a jump works differently, right? Because a jump precisely values points, whereas the Lebesgue integral doesn't value changes at 1 point or 2 points, right? So fundamentally at t equal to S1, the first term doesn't increase, but the second term jumps by 1 because phi S1 is equal to 1, right? So at this point, this function is going from 1 to 0. At S1, this function is going from 0 to 1, right? So putting them together, you would get phi S1 is equal to 1. And consequently, you get a jump at that particular point. But then after that, both terms are 0. So after that, phi S will be equal to 0. And after that, both terms will then subsequently become equal to 0. So if you take all these behaviors together, what you get is this stochastic formula. So up till S1, the first guy is minus lambda t. At S1, this thing goes up by 1. This thing doesn't go up. And then after that, both do not go up. So it is just 1 minus lambda S1 after for large enough t. Right? Yeah. No, its behavior is contributing to the sum, right? Because at S1, what is happening? At S1, S1 is the first jump time of the Poisson process. So delta n at S1 is equal to 1. So at S1, it's jumping by 1. Before S1, it doesn't jump. After S1, it may jump. It will jump at S2, S3, and so on. But at those points, this function phi is 0. Because phi, if you remember what is phi, phi is the indicator up from 0 up till S1. So after S1, it is completely 0. We don't care at all, right? So because of that, this is the stochastic integral, right? Now, what happens if phi s, so this is what happens if phi s is indicator 0 S1 closed. What happens if indicator 0 S1 open is the definition? Now, it turns out that this is a martingale and we'll prove it. But if you replace indicator 0 S1 with indicator 0 open S1, then what happens? What happens is that you need to just focus on what happens at t equal to S1. At t equal to S1, what will happen is that phi S1 delta n S1, what is this quantity then equal to? If it is 0 comma S1 closed, then it will be equal to 1 into 1, which is 1. This is if you have S1 closed, right? But if it is S1 open, so if you have indicator 0 S1 open over here, this guy, then what will happen is that phi S1 will be equal to 0 because the indicator ends at S1, right? So because of that, you would get 0 into 1, which is 0. So you wouldn't get that jump at all. That jump would not happen, right? And if the one jump doesn't happen, then this indicator is completely not even there. It is not there. And you just get minus lambda min of t comma S1, which is obviously not a Martin. So you can see that it makes a difference whether you have left continuity or not. Now let me quickly show you why this guy is a martingale. What we do is we basically focus on two different parts. We focus on one part where we deal with what happens if S1 is less than equal to S, and we deal with S1 greater than S. Now, if S1 is less than equal to S, you will take a look at this martingale and see how it behaves. Okay. First of all, what have you done? You want to take a look at T greater than S. So for T greater than S, you want to take a look at expectation of MT given Fs, right? Where Fs is the filtration with respect to which NT is there, the Poisson process. Now, you look at MT indicator S1 less than equal to S, which is basically until the first jump. Now, until the first jump, take a look at what is going on over here. What is going on is that the probability that S1 is less than equal to T given Fs is then obviously 1 because S1 has already happened. So obviously S1 is less than equal to T. And the second one, T minimum of T comma S1 is also just S1, right? But now you take a look at this guy, and this guy turns out to be a martingale. Why? Because 1 is the same as N minimum of S comma S1 because S1 is less than equal to S, and lambda S1 is the same as lambda min of S comma S1 because again S1 is less than equal to S. So if you think about it, this is nothing but NT minus lambda T, which is the martingale that we already know. But instead of T, you have T replaced with a stopping time, minimum of S comma S1. So a stopped martingale is also a martingale, right? That is something we know, which means that this guy is also a martingale. So MT indicator S1 less than equal to S is a martingale. And therefore, this guy conditioned on Fs should just be equal to MS indicator S1 less than equal to S. Now for the second guy, things change slightly, but not too much. What will happen is that if S1 is greater than S, then what does it mean to condition on Fs? Remember, Fs is the information about the Poisson process. So if S1 is greater than S, the only information that you know is the Poisson process hasn't jumped. It's constantly 0. That's all you know until time is, right? So you know that S1 is greater than S. That is pretty much the only information that you know. So this guy, the first guy, the indicator part, is just 1 minus the probability that S1 is greater than T given S1 is greater than S, which is just, you know what it is, exponential random variables. The second guy is a little bit harder to compute, but you can see that if S1 is greater than S, then again, conditioned on S1 greater than S, S1 still remains an exponential random variable. So you just get this particular density, right? This is nothing but the probability that S1 is greater than U given S1 is greater than S, right? E to the power minus lambda times U minus S. And this is just minimum of T comma U. So you're just using instead of S1, you're taking S1 equal to U. So minimum of T comma U, E to the minus lambda U minus S du. You need to integrate from S to infinity because S1 is greater than S. Just do this integral. Once you do the integral, you just get this guy. Now you combine this with this, and the E to the minus lambda T to the minus S cancels out. The 1 cancels out, right? And you'll just get lambda minus lambda S. That's exactly what you, right? And it turns out that this is exactly equal to what the original guy would have also been at this point. So MS indicator S1 greater than S. If you go back here, MS indicator S1 greater than S is also exactly minus lambda S, because the first indicator will be 0 and the second thing will be minus lambda S, right? So a little bit of a complicated computation, but you can see that you do in fact get a martingale. So this guy Over here, this is actually a martin. Now, quadratic variation. Before we go to the Ito formula, we should talk about quadratic variation. Right? How does this work? Well, it turns out that if you have a jump process, the only thing that happens is that the jump itself contributes to the quadratic variation, but the so-called cross terms don't contribute. So in other words, if I deal with, the typical definition of a jump process and the typical definition of the quadratic variation, then you get the Ito part, the typical Ito part. But in addition, you also get this interesting term, right? And we'll understand where this comes from. This basically comes because of the usual argument that you use to eliminate the drift. So if you have the drift over here in X, the Ito part of the drift part of the Ito process, the reason why that doesn't contribute to the quadratic variation is, if you remember, there is this max of thing that you take out, right? You take out the maximum variation and that goes to 0. There is some argument around that, right? This is nothing but a repetition of the exact same argument. So if you have the continuous part, gamma t dbt plus theta t dt, you take a look at, so see, when you are squaring this quantity, xtj plus 1 minus xtj, the whole squared, you write xt as xct, which is the continuous part, plus the jump part, which is jt. So you just apply the typical formula, right? A minus b whole square is a square plus b square minus 2ab. Now what's going to happen is that this a square is going to contribute to this. This b square is going to contribute to this. And this minus 2ab, if you just take the 2 out, just the ab part is what we're dealing with over here, right? So summation j equal to 0 to n minus 1, xctj plus 1 minus xctj into jtj plus 1 minus jtj. Just as usual, take out the maximum. Take out the maximum. The rest are being summed. Now this guy, whatever this sum is, this is finite because j is jumping almost surely only finitely many times in between 0 and s, right? This goes to 0. Why does this go to 0? Because this is something fixed or bounded. And this guy is a uniformly continuous function, right? So it's a uniformly continuous function, which means that its maximum variation as I let the partition become finer and finer goes to 0. So this goes to 0, which means that the quadratic variation is going to only depend upon the quadratic variation between the continuous part and the quadratic variation between the jump part. Now this quadratic variation we already know is equal to the Ito thing. So we only need to focus upon the jump part. And the jump part is pretty obvious because if you just take a look at what this summation is, now just think about it, okay? You have a jump process which is jumping at different points, right? If I take a partition which looks in black, let's say, then I only need to look at parts of the partition which are in between jumps, right? So for example, in between these 2 points, jtj plus 1 minus jtj is just equal to 0. But in between these 2 points, jtj plus 1 minus jtj is equal to the value of the jump, right? Whatever this jump is from here to here. Right? So we know that the partition eventually, when it starts becoming finer and finer, because this process has only finitely many jumps, eventually one jump will get captured in each partition. So ultimately, if you let A be the set of indices where it has a jump, then this sum is nothing but you take a look at how much it changes within each partition and you add up the sum of squares over each jump. Makes sense. But as this partition becomes finer and finer, as I said, the jumps are discrete. So every jump will eventually be captured in a separate part, which means ultimately this sum will converge to every possible jumps square, which is the basic idea behind what is. Now, just like you define the quadratic variation, you can define what is called the quadratic cross variation. This Sandeep did not do this for the Ito process, but what you can do is instead of taking a look at instead of taking a look at xtj plus 1 minus xtj whole square, if you have two different processes, it's like taking the inner product. Instead of taking the norm, it's like taking the inner product. So you do this instead, right? If you have two different processes, x1 and x2, you take a look at x1 tj plus 1 minus xtj1. So just how much this guy is changing in that interval minus times how much the other guy is changing in the same interval, right? So you take this cross variation, and now there's something very surprising that happens. The cross variation between a Brownian motion and a Poisson process turns out to be 0, right? In fact, it's basically because if you go to this definition that you see over here of the cross variation, it will turn out that exactly the same thing will happen. If you have any two processes, any two jump processes whose decompositions are given like this, then their cross variation will exactly turn out to be gamma 1s gamma 2s ds plus this sum over delta js1 times delta js2. This is the logic for this is very similar to the thing that we did before. All the cross terms will vanish. The Ito terms will combine like this, and the jump terms will combine like this. Now for a Poisson process, this guy is equal to 0. So if you're looking at b comma n, where b is a Brownian motion and n is a Poisson process, for a Poisson process, this guy will be equal to 0. This guy we don't care. We know it's something, but we don't care. For a Brownian motion, this guy will be equal to 0 because it doesn't jump. And this guy is not equal to 0, but we don't care. So ultimately, this guy b comma n will just be equal to 0 plus 0, which is 0, right? So the cross variation between a Brownian motion and a Poisson process on the same space is actually equal to 0. Surprisingly enough, this actually is contributing to a very interesting fact. A Brownian motion and a Poisson process on the same filtration must actually be independent of each other. So in other words, if I give you a sample space and I run you a Brownian motion on that space and a Poisson process on that space, then they actually have to be independent of each other. You cannot create a Poisson process that is dependent on the Brownian motion. You cannot create a Brownian motion that's dependent on the Poisson process without changing the filtration. So if you do change the filtration, then it's possible. But if you force them to be on the same filtration, then it's not possible, right? So in more generality, if any two processes have cross variation 0 and they're on the same filtration, they must be independent. Now, let's take a look at the Ito-Doeblin formula. So the Ito-Doeblin formula is basically nothing but the Ito formula with jumps. And as you can imagine, it's not going to be very difficult. Just the typical Ito part, and the jump part is going to be something relatively straightforward, right? Now let's take a look at just the Poisson process NT. Let's not deal with jump processes in general, just the Poisson process, right? What can we say about f of nt, where f is some function? So maybe nt square, or maybe e to the power n, right? Something like that. Sorry. What we can say is the following. See, nt itself is a process which behaves something like this, right? So it jumps independently exponential. Now, if I'm taking f of nt, until here it's 0, until here it's 1, until here it's 2, until here it's 3. Now, this is what is nt. If I look at f of nt, you would not be surprised that up till here it's constantly f of 0. Then for some time, it is constantly f of 1. Then for some time, it is constantly f of 2. Then for some time, it is constantly f of 3. Then for some time, it's constantly f of 4. Then for some time, it's constantly f of 5. So you see that it's basically the same property. It's also piecewise constant and right continuous. Because nt is right continuous, f of nt will also end up being right continuous, right? So because of that, it should not surprise you at all that if nt doesn't jump, f of nt is piecewise constant. And when nt jumps, then f of nt jumps. But the value of the jump is the difference of the function values at the left and right limit, right? So for example, the jump from f from 0 to 1 over here is 1, but the jump here is f1 minus f0, right? The jump here is f2 minus f, right? And so on. So the jump values are different, but otherwise fundamentally it's just a piecewise constant function which is jumping. So because of that, this, so f of nt is just summation 0 less than s less than equal to t of the function value changes, which is nothing but, there is a bracket here, sorry about that, the value at the right limit minus the value at the left limit. Now f is right continuous, so the value at the right limit is just f of ns, whereas the left limit, as you can see, is the limit as you approach from the left of f of that value. So it's basically the value at the previous guy minus the value at the current guy. That's all, you're done. So this is also a pure jump process. And we already know how the continuous part behaves. So the jump part behaves like this and the continuous part behaves like this, like the Ito rule. So you should not be surprised at all if the Ito-Doeblin rule looks like this. So if you have a jump process and you have f prime and f double prime continuous, as in the typical Ito rule, then you have the red part, which is the Ito part, and you have the blue part, which is the jump part, right? So the jump part I have already explained to you, and the Ito part is already something that you have seen previously, right? This might look a bit complicated, but once you unravel it, so let's say you take xt as the Brownian motion, then this is basically nothing but the usual formula for the Brownian motion, right? Where dbs into dbs will be equal to ds. Don't forget. That's how it works for the Brownian motion, right? The box rule of it. How is this proved? Again, it should not be surprising to you at all the way it is proved. What you do is that between any two jumps, you apply the typical Ito's formula. So suppose you have u less than v and there is no jump between these two guys, then the typical Ito formula will tell you that fxv minus fxu is the typical Ito expansion, which is this, right? But now suppose you include jumps into this, what you will be doing is you will be assuming that u and v are between two jumps. The first one is called tau I, the second one is called tau I plus 1, or let's say tau j, sorry, I think I called it j in the next slide. And what I'll be doing is I'll be letting u go to tau j from the left, from the right, and v go to tau j plus 1 from the left. So one of them is approaching from the right, one of them is approaching from the left, right? So u is going down to tau j, and v is going up to tau j plus 1. Keep this left-right business in mind. And if you take just the continuous part, then this formula holds because the continuous part is not jumping, not going anywhere, right? But the jump part, if you take the limit, then as v goes up to tau j plus 1, that jump must be included in the, if you're integrating up to and including the endpoints, then that must be included, right? So you just get this and you're done. So this really should not be too surprising, this particular rule. Now what we'll do is we'll apply this to a particular scenario. Right. Now let's take a look at this process and we'll try to show that this process is a martingale. And what will we do? We will show that it's a martingale by showing that it's a stochastic integral with respect to a martingale of a left continuous adapted process, right? Which is how we would typically operate in this setting. Now, take a look at this process and tell me, here sigma greater than -1 is a constant. If sigma is less than 0, then does this process move up or down between jumps? Can someone tell me? If sigma is less than 0, if it's a negative number. So imagine that nt is fixed. what is happening to the process as t is going up? Nt is now fixed. Like take Nt as 1 or 2 or 5. What is happening to the process? Sigma is negative. Make this easier for yourself. Just imagine Nt is not even there. Like, because between jumps, this guy is not even there, right? What does this function go up or down if sigma is negative? Goes up, right? Because sigma is negative. So this negative into this negative gives you a positive number. So you get S naught x of some positive number into t. So as t is going up, positive number into t is going up, x of that is going up. So if sigma is less than 0, then st moves up between jumps. Now, does this function jump up or down? Every time it jumps, does it jump up or down? Jumps up or jumps down? It's a martingale. So now tell me. Exactly, right? So if it's going up in between jumps, it's a martingale, so it's mean reverting. So it should jump down, right? And how do you prove that? You prove that by noticing that sigma is a negative number, right? So sigma plus 1. So sigma is between 0 and 1. So sigma plus 1 is a number between 0 and 1. So its logarithm is a negative number. So this is basically something like minus nt effectively in that case, right? Which means that as nt is going up, minus nt is going down. So exponential of minus nt is going down. So it jumps only down. And similarly, the opposite happens if sigma is greater than 0. So then st moves down between jumps and jumps only up. Right? So very interesting. Sigma is a positive and could potentially be a negative parameter. Now, what we will do is we will apply the Ito rule to this. And we'll apply the Ito rule in the typical fashion that Sandeep applied the Ito to the exponential Brownian martingale. So we will take S naught f of xt, where f of x is e to the power x and xt is whatever is on the exponent, nt log sigma plus 1 minus lambda sigma t, right? So what we do is we separate it into its, separate it into its jump part and its continuous part. There is no Brownian part. Keep that in mind. So because of that, the continuous part is minus lambda sigma t and the jump part is just nt times log of sigma plus 1. So this is your Ito rule applied to that, right? Because as you can see, xt, so dxt is equal to minus lambda sigma dt plus sigma plus 1 dnt. This is exactly what it's equal to, right? So if you just combine this, then what you see is that f of xt is f of x naught minus lambda sigma, this integral, plus this sum. Right? That just follows directly from the Ito-Doeblin form. Now all we have to do is we just have to make this a stochastic integral with respect to a martingale. So all we need to do is we need to observe a couple of things over here. The first thing we need to observe is that at any point, you just think about how much this guy jumps. Okay, delta f at xu. Now at any point at which this jumps, when it jumps, this guy doesn't jump, right? So this guy, we're not bothered about it at a jump. But when this guy jumps, you get a sigma plus 1 multiplied on, right? Because nt is going from one value to the next value. So this particular guy jumps by exactly log of sigma plus 1, which means that exponential of log of sigma plus 1 is just sigma plus 1. So a number, whatever it was initially at the left point, at the right point, it will get multiplied by exactly sigma plus 1 of itself. And therefore, the change will exactly be sigma times the left value, whatever it was on the left. Right? So this holds. If I just take a look at this guy, this is just equal to summation 0 less than u less than equal to t of sigma times the left limit times delta nu. Right? And thankfully, because of what we know about stochastic integration with respect to the Poisson process, this is nothing but summation of f dg, where f delta g, where g is the Poisson process. So this is nothing but integral of f dg. This will be useful because we'll be bringing in a martingale. Now, at the same time, f of x is e to the x. So that means that f prime is equal to f. So just apply these sequential rules that you see over here, right? So f prime of xu will just be equal to f of xu. I'm just bringing this lambda sigma inside the du to make it sigma lambda du. And this delta f of xu, I have already, as done in the previous slide, written it in this form. Now you can already see what's going to happen over here. What's going to happen is that this is a integral that is being done with respect to Lebesgue measure, right? If I integrate a function with respect to Lebesgue measure and I change the original function at some finite number of points, the Lebesgue integral doesn't change. Now this function and this function, which is a function and its left limit, only will differ at finitely many points because this function only jumps at finitely many points. So because of that, this integral and this integral are exactly the same. And these two integrals, there's no change between them. But now all I need to do is I just need to combine the two integrals over here. And you can see that this to this step to this step is then obvious. And this is a martingale. So you are integrating a left continuous function. So remember, you're taking the left limit of this function that will end up being left continuous. And a left continuous function is being integrated with respect to a martingale. Because this, once you take out the sigmas, this is nothing but nt minus lambda. So nothing but a martingale, and you are integrating a left continuous function with respect to it. Ergo, this original guy, f of xt, is also a martingale. And if you're just multiplying it by a constant s0, that is still a martingale. Right? So it's a bit complicated, as you can see. But what is the basic idea? The idea is that the fundamental martingale that is associated to the Poisson process is nt minus lambda t. So we will keep coming back to this guy. Right. Girsanov's theorem. Now, Girsanov's theorem is about change of measure, right? What we have is a process that behaves in a particular way, and we want to change it so that it behaves in a different. Now, if you recall the typical Girsanov's theorem, what we do is we eliminate drift using Girsanov's theorem, right? So if we have this extra random drift that is there over here, gamma SDS, we take a process which has that drift and convert it to a Brownian motion by changing the measure using a multiplicative object zt. So Q of A is expectation of zt indicator A with respect to P, of course. Then this Q ensures that this process B prime is a Brownian motion and things become nice for Brownian motions, right? Now for jump processes, why should we need Girsanov's theorem? What is the nice object which we want to revert towards, right? And the answer is, unfortunately, now I know some people might say, oh, I wish we could take everything back to a Poisson process. That's nice. As it turns out, that isn't quite possible. The only thing that you can do is, if you're given a Poisson process of a certain intensity, you can at least change that intensity. So if you have a Poisson process of intensity 2, you can change it to intensity 1, intensity half, right? And typically, if you're on a computer and you have a Poisson process that's of intensity 10 to the power minus 8, you obviously will not be able to simulate it with that much accuracy. You want to change 10 to the power minus 8 to half or to 2, more realistic. So you can do that using Girsanov's theorem. And the other option is, if you have a compound Poisson process whose jump distribution is weird, maybe it jumps too little or too much, and impossible for a computer to simulate, guess what? You can change the jump distribution, but some caveats are, which I will bring, right? We'll start with the first one for now, how to change the intensity of a Poisson process. So let NT be a Poisson process with intensity lambda, and you want to change NT to having intensity lambda prime using a different measure Q. So how can we do this? What we do is, we just notice that what do we fundamentally have to do? See, typically NT is Poisson lambda T under P, right? We want NT to become Poisson of lambda prime T under Q. So what we want is, we want Poisson of lambda T to become Poisson lambda prime T, right? So what we need to do is, we need to interpolate between these two guys in the process of creating this measure Q. And what the next process is going to do is precisely that. Let's take an example, right? So if you have lambda prime as 2 lambda, we basically want to have twice as many arrivals, right? Because if you increase the intensity by 2, you're increasing the number of people that arrive per unit time or whatever by 2. So if NT has fewer arrivals, you weigh this less. And if it has more arrivals, you weigh that more. So if you take a look at ZT over here, that is doing precisely that. What it is doing is, it is saying that if lambda prime is 2 lambda, then you get 2 to the power n of t. So if n of t is bigger, that is a bigger number. And lambda minus lambda prime t tells you that as time is going longer and longer and longer, you're compensating for the fact that inter-arrival waiting times are being cut down by half each time. Right? So this is what the Girsanov's theorem tells you. It tells you that this ZT is exactly the correct change of measure. Right? And we'll actually prove this. We'll prove this in the next slide. But what we won't prove is that this ZT is in fact a martingale. We won't prove this. This is because it's just a repetition of the same machinery that we've seen before. So I won't prove. Now, what is the proof idea? I said that you should match the Poisson process. Poisson of lambda t should get matched to Poisson of lambda prime t, right? Now, what we'll do is, in order to make the transition as easy as possible, we'll match the moment generating instead of matching the exact PMFs, right? Which is what you would logically expect from us. So let's match the moment generating functions. For that, a very quick calculation shows that the moment generating function of a Poisson random variable is given by this form. And you can see how it works. If you just take expectation of e to the power un t, just write it using the typical formula, expect e to the power un times the PMF of a Poisson random variable nt. Then what happens is that this e to the power un and this lambda t to the power n, both of them get combined. So you just get e to the u lambda t to the power n. And this is nothing but e to the power x is summation x to the n over n factor, right? So this just leads you to this form. So e to the power e to the u lambda t minus lambda t. The minus lambda t is lying outside. So now we just have to change the MGFs. We just have to see that multiplication with ZT is changing the MGFs. And this is exactly what happens. So if you just take a look at the left-hand side, we've now multiplied with ZT, which has affected the change of measure. And if you recall what is ZT, ZT is e to the lambda minus lambda prime t times lambda prime by lambda whole to the power nt, which is exactly what we've done over here. The e to the lambda minus lambda prime t is deterministic. I have pulled it outside. Whatever is left is I have kept it inside the expectation. Now I'm taking the power of something times nt. What is that something? You can clearly see that lambda prime by lambda to the power nt is nothing but e to the power nt into log of lambda prime by lambda, right? This is just the typical, product rule or whatever for logarithms, right? So this becomes e to the power u nt into e to the power nt log lambda prime by lambda. So you just get e to the power u plus ln lambda prime by lambda times nt. So you just go back to this formula. In this formula, you replace u with u plus ln lambda prime by lambda. That's exactly what I have done over here. And then some algebraic recombination leads you to the correct MG. Lambda is now replaced by lambda prime. So under this change of measure, an originally Poisson lambda t random variable has become a Poisson of lambda prime t random. And now once all the marginals have changed, it's just a technical fact that the process still remains a Levy process, and Levy processes are actually identified by their one-dimensional distributions. So basically, if there is a Levy process and I tell you that every marginal is Poisson lambda t, it is actually uniquely the Poisson process with intensity lambda. This is a non-trivial fact. I won't go into it. Right? So this works, and this is why Girsanov's theorem works. Now, what about jump distribution? This is where something very interesting happens. So now someone might say, what happens if I want to start a Poisson process which jumps by 2 each time instead of 1? Turns out that this can't happen. You can't do this using a change of measure. So if you want a Poisson process that originally is jumping by 1, and you want to make it into a Poisson process that jumps by 3 each time instead of 1, or that jumps by -1 each time instead of 1, you can't actually do that using a change of measure. Why? Because if you think about it, change of measure for us, it's tantamount to having a Radon-Nikodym derivative in place, right? So basically, we have the fact that the two measures are on the same space. You cannot have a measure on one space, a measure on another space, and then have a change of measure between them, right? So these two processes, so for example, if I take a look at NT, like this is a typical path of NT, right? It jumps by 1 each time. But if I take a look at 2NT, fundamentally, this is a process which is jumping by 2 each time, right? So all these gaps are 2 instead of 1. And it's not possible because anything that can be a sample path of NT cannot be a sample path of 2NT. And anything that's a sample path of 2NT cannot be a sample path of NT because their jumps are fixed, right? So in order to do this, you must have some correlation between the amounts that each guy jumps. And in particular, what you can do is, if you assume that the support of the jumps doesn't change. So if you're changing NT to N prime T, you should ensure that the compound Poisson part of NT, where all NT can jump, should be exactly the set of points where N prime T can jump. So it cannot happen that here the jump size is 1 and here the jump size is 2. It can happen that here sometimes it jumps 1 and 2. Sometimes here it can jump 1 and 2. So that is okay. But it cannot happen that the jump sets are completely disjointed. Right? Now, what can you do? Loosely speaking, we'll do marking. Okay. So I'll tell you, if you recall how marking works, you can basically track when each jump occurs, right? So if we're calling a jump as good or bad, what we're basically doing is we're basically tracking each jump value. So we're saying jump of value 1 is good, jump of value 2 is bad, or something like that, right? Now, if I mark each jump by itself becomes a Poisson process. So we have multiple Poisson processes for each jump which are going on. And for each of them, I'll change their intensity. So if I make one jump more intense and more frequent compared to the other jump, then I'm changing the jump distribution effectively by saying this guy is more frequent, this guy is now less frequent. So the ultimate jump distribution will tilt towards one guy against the other, right? And that's basically what we're going to do. We just need to mark each jump, which is a separate Poisson process. We'll change the intensity of that jump. So if you want to make it more frequent, we'll make the intensity higher. If you want to make it less frequent, we'll make that intensity lower, right? And then later on, we can stitch all the jumps together. Now, this is the formal description. The informal description is actually much easier. Sorry, this is the informal description. The formal description is like this, right? If you have a jump J, which is originally happening with probability P, let's say, in a Poisson process of intensity lambda, by itself, its intensity is lambda P. So if lambda people are arriving every hour and half of them are bad, then half lambda bad people are arriving every hour, right? Now, what we want to do is, suppose we want to reduce the number of bad people, we want to pull it down, we have to pull down the intensity of that Poisson process. So to pull down the intensity of that Poisson process, and if we want to pull down the jump probability to Q, what we want is, we want lambda prime by lambda to the power mt to basically become lambda prime q by lambda p to the power nt. That's all that's going to happen. And this is for discrete jumps, like this is for one jump at a time. The formula in more generality is also able to cover continuous jump measures. So basically, suppose that you have a compound Poisson process with certain jump density f. You want to convert the jump density to g. Then what do? You basically change the intensity to lambda prime in a manner such that you are now not having, so for that particular jump, yi, you are having lambda prime g divided by lambda f. But different jumps happen at different times. So for each jump, you account how many times that jump is happening, and you are multiplying by that particular product. So this is the appropriate change of. So actually under this measure, you get a different Poisson process with a different intensity and a jump distribution g until time. So you can do a Girsanov for just change of intensity, and you can do it for change of jump, provided that you're not changing the fact that g of y is 0 if f of y is 0. So if the original process cannot jump length 3, your new process cannot jump length. That's all. Right? Now, Girsanov for jump processes, which I won't explain, basically states that, now what helps here? What helps is that the Brownian motion and Poisson process on the same space are independent. We've actually seen this, right? I mentioned this as a fact. So because of that, if you're just performing a change of measure, just change the Brownian motion separately and change the Poisson part separately, right? So you just consider the product of the Poisson change of measure and the Brownian change of measure. And this will get rid of both the drift. So it will convert B prime into a Brownian motion, and it will convert the intensity of the associated QT and jump density G. So everything can be done. And this is the most general Girsanov for jump process. By the way, there's something very interesting. It's pretty difficult to believe, but this theta t can actually depend on QT. So if you have a drift, you can actually make that drift depend upon QT, but you can ultimately convert it to a Brownian motion, which doesn't depend upon QT. Doesn't depend on independent. Now, let's take an example of Girsanov's theorem. Suppose you have a process that is your usual guy. Okay, we've already seen this before. And by the way, this thing has a name. It's called the geometric Poisson process. So just like how you have geometric Brownian motion, you have the geometric Poisson process. Now, what does the word geometric mean? It always means the same thing. If you have a stock price that's going up or down, then the amount by which the stock changes at each point is typically a multiple of the original stock amount, right? So stocks change by percentages, not by additions and subtractions. That's the basic idea. So the geometric word captures that particular property. This is very similar to the earlier process we saw. In fact, the earlier process we saw was exactly this process without the alpha, right? If I take out the alpha, then ST is S naught x of NT log sigma plus 1 minus lambda sigma t. This is exactly the same process that we saw earlier. And we saw that that was a martingale. Now, what about this guy? This guy is not going to be a martingale, obviously, because ST into e to the power alpha t is a martingale. So this guy is a guy that's either up or down. So it's either a sub or a super martingale, one of the two. But we can exactly find out what it is based on alpha, right? So what we'll do is we'll apply the typical Ito-Doeblin formula in order to figure out what this is. So we'll write ST as S naught f of xt, where now xt is this process along with the alpha. And we'll just repeat the same steps that we did earlier, right? Just repeating the same steps that we did earlier. So f of xt still has the same property, but you have an alpha minus lambda sigma over here instead of just lambda sigma. And the second part is still the same. So this observation that we made last time, same as this time, right? Also f prime is f because f of x is e to the x. So the only thing that changes is that this alpha part is getting multiplied with, so f prime is nothing but f. So alpha into integral 0 to t f of x u du. And then the rest is exactly what we've seen before. So this is the only thing which involves alpha. So you just get alpha integral 0 to t f of x u du. And remember that the right hand side is also f of x t only. So you just get dst is alpha st dt. This is what you get from here, alpha st dt plus the remaining martingale part. So this is your drift in some sense. And this is the volatility sigma, which is fluctuating around. Now, if I want to use Girsanov, what I want to do is I want to change this alpha. And when I explain the finance example, I'll explain why it's important to change alpha. We want to change alpha to some number r. And the wonderful thing about the demonstration that I'm going to give you in the next slide is that it turns out that not all r's work. So if I want to change alpha to something, I cannot change alpha to anything, unfortunately. I can only change it to a number that depends upon the intensity of this Poisson process. Now, what is going to happen is that you are going to do this by changing the Poisson process intensity. So you're not going to change there is no jump density, there's no compound Poisson process here. There's only the Poisson process. You're going to change its intensity. And once you change its intensity, you'll hopefully hope to change alpha to r. So what we'll do is we'll focus upon the effective drift term. Now, what is the effective drift term? Over here, you have alpha st dt. That comes from here. And then from here, you have sigma minus lambda sigma st dt, right? So alpha st dt minus lambda sigma st dt. What will happen is that this quantity will have to change from alpha minus lambda sigma to r minus lambda dash sigma, because lambda will change to lambda prime. You'll get a new intensity, and alpha will change to r. So if these two have to be equal, which is how we'll get the changed intensity value lambda prime, we just set them equal, and we get lambda prime is equal to lambda by sigma minus alpha minus r. But you see that this quantity has to be positive. If the intensity is negative, it makes no sense, right? So for it to be positive, not all r will work, right? So you require lambda by sigma minus alpha is greater than r. This is basically what you require. So r cannot be too large in some sense, right? This is exactly what it is. So otherwise, I know that I just have to change alpha to r. So I just need to change lambda to lambda prime. And therefore, I know precisely what Girsanov achieves, that is just e to the power lambda minus lambda prime t times lambda prime by lambda into nt. So under this, what will happen? That martingale nt minus lambda t, it will get converted to nt minus lambda prime t, right? And this alpha will get converted to r. So you'll just get this one. And once this is true, then what is a martingale associated to this process? We've already seen what happens over here, right? What happens is that if you have this situation, then e to the minus alpha t st is a martingale, right? So if you take out alpha, you get a martingale. So over here also, in this process, if I take out the r, then I should get a martingale. And how do I take out the r? By just doing e to the minus r. So just alpha has taken the place of r. So there e to the minus alpha st was a martingale. Here e to the minus rt st will be a martingale. Right? So you can see how we can get new martingales under new measures. And this is precisely where the finance application comes. This is the discounted stock. So let's see. So what we'll do is we'll consider the stock price process given by the geometric Poisson process. So if you remember, this is trying to be a martingale, but now because of the alpha parameter, it is no more a martingale, right? So let us try to price a European call option. Now, if you remember, how does a European call option work? What you do is that right now, I will pay a certain amount to buy a stock at time t for price k, right? So therefore, By then, if the price is less than K, obviously I will not buy it. I will not exercise the option. So in that case, my gain will be 0, right? But if the stock price goes above K, and if I assume that I'm just buying 1 unit, then my gain over that 1 unit is that, oh, I should have bought it for ST, but my option allows me to buy it for K. So I gain ST minus K for that 1 unit, right? So my payoff or my gain for this option is max ST minus K comma 0. So if I get the option for free, this is my payoff. Obviously, I'm not getting the option for free. I'm asked to pay some amount for that option. So what should I pay? What's a fair price, right? And the answer is that in order to have a fair price, we should talk about a competing bond, which we can use to hedge our strategy, right? So unless and until we are able to account for the fact that we can generate that money in an alternate manner, we cannot talk about fairness, right? So we consider on the side a fixed bond with a return rate R, so that it will have ST is equal to S naught e to the power RT. So that's a fixed bond which will give us R percentage return every year, right? Now, to compare both, we are basically considering the discounted stock price, like you were saying, right? So e to the minus RT ST is basically nothing but the ratio between the stock price and the fixed bond price, right? It's nothing but the ratio between them. So for things to be fair, somehow the rate at which that fixed bond is increasing has to be compared to the rate at which the stock price is fluctuating on average. So we take their ratio, which is what it means to discount, and that gives you this quantity. So it just gives you alpha minus R minus lambda sigma into T. And we've already seen that e to the minus RTST is a martingale under the measure Q. So Q is a risk neutral measure. Q is the measure under which the fixed bond is giving you no returns. What you want is you want to have to make a decision between the stock and the bond. So you want ideally your payoff constantly to also be a decision to make. So you want that to be a martingale, because a martingale ensures fairness throughout. So what should happen is that e to the minus RT into VT should be a martingale, right? The discounted payoff. So what you get from your option compared to what you get from the fixed bond should be comparable. You should have a decision to make, which means that this discounted payoff should be a martingale. And if it's a martingale under the risk neutral measure, then this formula holds, right? Because as you can see, this is nothing but the process at time t, and this is nothing but the process at capital time t conditioned on all the information up till time small t. Right? And we know what is the payoff at time capital T. That's just max of ST minus K comma 0 given FT. Right? So we've gotten a risk neutral measure. We have a notion of payoff. We have a option pricing formula as well. Right? Now, how can we calculate this right hand side? The rest of this lecture basically focuses upon that, and it's not very difficult. Basically, the idea is you need to figure out how to condition on FT. That's the only way you can get an explicit formula. But thankfully, this guy, ST, has an explicit formula. So if you just go back to ST and its definition over here, then you can easily see that. So if you take a look at ST, ST is equal to S naught e to the power NT into log of sigma plus 1 plus alpha minus R minus lambda sigma, right? Oh, sorry, I'm looking at just ST. I'm not looking at e to the minus R. It's just alpha minus lambda sigma, right? So what will happen if I go ST, like basically if I look at this guy, ST divided S capital T divided by S small t, I'll just have R minus lambda tilde sigma under the discounted, remember, under the changed measure Q, alpha has become R and lambda has become lambda prime, right? So you will just get this guy, sorry, what have I just done? You will just get r minus lambda prime sigma over here instead of alpha minus lambda sigma. And therefore, r minus lambda prime sigma into capital T minus small t will come over here. And over here, you will get n of capital T minus n of small t into log of sigma plus 1, right? That's basically what will happen. So this will be equal to S capital T divided by S small. Right? So this formula is exactly what you do. And therefore, you get, once you just take this e to the minus RT to this side, you get this particular big form. Now, again, we still haven't conditioned with respect to FT, but you can see that this process is breaking into two parts. One part is the part which is NT minus NT, that part, and one part is the ST part. Just ST alone is FT measurable. Everything else is independent of FT, independent of FT, independent of FT. This is independent of FT because NT is a Levy process, right? Which means that N capital T minus N small t is independent of FT. So everything that happens before time t, everything that's happening after time t, independent. So now what we know that Vt is a function of two guys, something that's measurable with respect to Ft and something that's independent of. And for these guys, for such functions, there is a very specific formula for the conditional expectation, right? I think Sandeep taught this, but I'm not too sure. So if you have expectation of f of, let's say, y comma z given x, where y is dependent on x and z is independent of x, this is actually equal to expectation. So this is nothing but a function of, so remember, this is a Borel function of x, right? So let's say I take conditioned on capital X equal to small x. This is nothing but f of, sorry, expectation f of small x, comma, sorry, not small x, y of small x, comma, z. So basically what you're doing is, if once capital X is fixed, if y depends on x, then capital Y will also get fixed to some value capital Y of x, and Z is independent. So you retain the expectation outside and just do the expectation over Z. So what you're doing is you're just separating it out into two parts. Whatever is dependent, you're fixing it. Whatever is independent, you're taking the expectation over. Right? And this logic tells you that, this is a very common result, by the way, for conditional expectation in this situation. It tells you that Vt is C of t comma st, where the x part, so if st is equal to x, then the st part gets fixed and you take the expectation over everything else with respect to q. Now this expectation is not difficult to compute because nt minus nt is nothing but a Poisson lambda capital T minus small t random variable. So you just apply the formula, typical, expectation formula. And what do we get? We just get, so we take this e to the power r t minus t inside. After having taken it inside, then you just get from here to here, it's just a definition of the Poisson random variable, right? So you have a Poisson random variable, which you replace with j, and then you take the density of j over here. Sorry, the PMF of j. And the PMF of j, because this is a Poisson lambda t minus t random variable, is just e to the minus lambda prime, sorry, t minus t to the power j divided by j factor. So this is some complicated expression, but you can see that this is an explicit formula for the option. So in other words, if I am pricing an option right now, and I am going to use that option at time capital T, if the time now is small t and the price of the stock right now is st, then the fair value of the option, the amount that I should have to pay now, is given by this infinite sum that you see over here. Right? So you can actually see this as well. So just to make sure that, if you want to do a sanity check, you can check that this sum, if you put small t is equal to capital T. So if you're trying to be fair at capital T, then this will become 1. This entire thing will become, except for, so only for j equal to 0, it will be 1. Everywhere else, it will be 0. Right? So what you will get is, you will just get the value for j equal to 0 over here. And that, if you think about it, so this t minus t will be equal to 0. This will just be equal to 0. So you'll just get maximum of S capital T minus K comma 0. That's exactly what you will get at time. So the fair price that I have to pay at time capital T is exactly the amount that I will have to gain at capital. So that is just establishing fairness at the end point. We already had fairness at the start, and this formula is telling us how to establish fairness in the middle. Absolutely in the middle, this pricing formula allows us to price options for stocks which possess jumps. Now, for stocks which possess Brownian motion and jump parts, it is much harder, because there you have to effect a change of measure, which will be given by this formula, right? It will be given by the combined Girsanov formula, where you will want to change a drift to a Brownian motion, and you will want to change a Poisson process into a different intensity Poisson process. So though that is much more difficult, and I won't go into that. But through these 2 lectures, what I've wanted to basically explain is jump processes, why they are important, how they basically behave, how you can change the intensity of jump processes, how you can stochastically integrate with respect to them, how you can perform a change of measure via the Ito formula. Sorry, a change of, what is it called? You can take functions of jumps basically using the Ito formula, and how you can change measure using the Girsanov formula. And for the simplest example, so this model, by the way, was considered in Merton's paper in 1976. So this and more fundamental following work won him the Nobel Prize in 96. And what we've just seen is a glimpse of that Nobel Prize winning work in the context of option pricing. Of course, now you might ask, well, how do I compute this infinite sum? That is a thing in and of itself. You can do it by approximating this entire thing using a partial differential equation, and finding the solution to that differential equation and taking its values at certain points. That is something that I won't probably explain. Okay, we're 2 minutes early, but I think it's worth ending today's class. Thank you. You basically assume that the lambda prime is becoming higher and higher and higher and higher. So what happens is that you're destroying the jumps of the process, and the C of t comma st almost becomes like a continuous time process. Continuous time, continuous process. Then that ends up satisfying a PD. Yeah, exactly. Great. Yeah, thank you, everyone.